let's start with the third question. Question 3, or question 4. Sorry, question 4 is mode plot. Let's skip that because I already did that in the midterm. Question 5, three-phase circuits. Finding information for three-phase online is really annoying. I don't know why. I can you tell I'm a little bit tired about it. Anyway, transform the source from delta configuration to Y configuration. So what it wants you to do, it wants you to turn. You can see it's called a delta configuration because it's a delta. And when it's a Y, it's because it looks like a Y. So let me draw the Y here. That's how it's going to look like. And I don't really have enough space, so I'm going to draw the delta on the outside here. So here we have the delta and the Y on the same sort of circuit. And just to emphasize that, I'm going to color in the Y with red. So let's do that. Oop. I should have done that from the start, but here you go. Red. There you go. Red. And the reds are all going to be pointing out. Let me just switch my brush size. There you go. So this here is going to be, okay, I made way too fucking big. Sorry. This here is VAB. Right? Because the positive terminal is pointing to A and the negative terminal is pointing to B. And you repeat that same process for all of these. So this, oh, sorry, let me paint this in red. Sorry, black. This here is VBC, and this here is VCA. So first thing that you have to do is, oh, sorry, and these ones inside, this point is N, it's neutral, right? It's effectively ground. So this is going to be VAN, VBN, and VCN. Sorry, let me draw, there you go, A, B, and C. You can see it matches A, B, C here. So first order of business is finding whether or not this is a positive or a negative system. I know there's like a mathematical way to do it, but I prefer drawing it out because it makes a bit more sense. Let's draw it out. Here we have our little graph here. So we are going to draw each one of these. So here is our VAB. So it's 25 degrees VAB. You can see here 25. Then we need, so we have VBC here, which is negative 95. 95, oops. Negative 95 degrees. This is VBC. And then this is going to be VCA. This here is 145. 145, right? Yeah, 145. They're all 120 degrees apart, right? So is this leading, or is this positive system, or is this a negative system? And what you do, it's very simple. So this is the direction of rotation. So if you can imagine in your head, I don't think this has a rotate tool, so I can't really show you, but it rotates this way. And this is what we're seeing right now, right? This is the power, this is the voltage that we're seeing right now when it hits that way. So you'll see VAB, and then it's followed by VBC, and then it's followed by VCA. Does everyone understand that? Because it's rotating counterclockwise. You see AB, then BC, then CA. So the order is A, B, C. Does everyone understand that? All right. ABC is a positive system as opposed to an ACB system, which is a negative. This AB, BC, and CA, as opposed to AB, CA, and then BC. So that's how you find it in a delta. If you're finding it in a Y, you do this exact same thing, just the first letter. So it's ABC, ACB. You really just look at the first letter. So ABC, ACA, B. So we can just move that. Yeah, there you go. So now that we find the positive, let's now draw out the information for positive. So for positive only, VAN is equal to what do you call the magnitude of V? Sorry, Jesus, I'm I'm a bit waffling here. Wait, no, it's correct. Never mind. So VAN is equal magnitude of VAN with a phase of 0. VBN is equal to magnitude of VAN with a phase of 120, negative 120. And VCN is equal to the magnitude of VAN, 120. How do you know if it's positive or negative? It does not tell you. It may tell you, here it does not. And I just showed you. So you need to draw out the diagram. You see here, this is the diagram that we drew out. There's VAB, VBC, and VCA. And the angles are from what's given to us, right? 25, 145, and negative 95, right? So we draw it out, and it will always be rotating counterclockwise. So from this point, right, we first see VAB, followed by VBC, and then VCA, right? You understand that? Yeah. So if it's A, B, C, it's positive. A, B, C. Yes. So you can see here B is in the negative area. There you go. Yeah, so it's going to be 0, B is negative 120, and C is 120. This is positive only. Now, if it's negative, it's the exact opposite. Or the phasors are opposite. That's all. I don't have a lot of space here. VAN is equal magnitude VAN with a phase of 0 degrees. VBN is equal to magnitude of VAN with a phase of 120 degrees. And VCN is equal to the magnitude of VAN with a phase of negative 120 degrees. What does counterclockwise have anything to do with this then? Because this system here rotates counterclockwise. And so this is our positive voltage. That's what we see. That's our real voltage that we actually see. So we see our VAB first, and then as it rotates, VBC is seen, and then VCA is seen. And then it repeats again, VAB is seen. You see what I mean? This is sort of our eye, right? This is what we see. Is this constant? Yeah. That's just fact. You have to memorize those. Okay. So now that we have that in check, actually, I drew this way too early. Let me move that down here, and then we can push this back up. So let's move that here. Okay, so now if you look at this diagram, right? What is VAN? We could do KVL across this, right? So from B to A, you know what the phase voltages in terms of phase voltages? To be honest with you, I don't really like this way, but I can't really think of another way to do it. Jasar does it like this. But you'll see why I don't like how it's written, but I couldn't think of a better way to write it. Just keep this in mind for now, right? So if we look at VAB here, this is equivalent to negative VBN plus VAN. Look at this here, right? We start at B, 2A is VAB, right? Now we start from B through VBN and then up through AVN, which is negative BN plus VAN. You're going to end up in the same spot. Does everyone understand how this equation is made? So, now that we have this equation made, kinda, yeah. So it's just showing two paths to get to it, right? We have the delta path, which is plus minus. This is VAB. This is B. This is A. Or we have the Y path. This is VBN and this is VAN, right? So this way is just VAB, right? This way around, if you do KVL, is negative VBN, right? Because we exit the negative side of the voltage source, plus VAN, because we enter the positive side of the voltage source. And because we start at the same point and end at the same point, these two are equal. Do you get it? There you go. See, now we're understanding it. Here, let me put this diagram up here. So, therefore, VAB is equal to VAN minus VBN. Now we substitute this data, right? We have the positive only. Let me just copy this and put this to the side here. This is going to be VAB is equal to VAN with a phase of 0 degrees minus VAN with a phase of negative 120 degrees. Now we isolate. That's going to be VAN bracket 1 with a phasor of 0 minus 1 with a phasor of negative 120. If you put that into your calculator, you're going to get square root 3 with a phasor of 30. I believe, yes. Go, put it in your calculator. 1 with a phasor of 0 minus 1 with a phasor of negative 120. Put that into phasor format. Square root 3 with a phasor of 30. Well, you know AB and you know VAN. You can now solve for, you know AB and you know this. You can solve for VAN. This is where I was saying that it gets a little bit weird, because at this point now you ignore this. Now you treat this never existed, right? So it's equal VAN, and also we remove these the magnitude. That's what I'm saying. This method is a little weird. I don't like it, but I don't know the other way to do it. Anyway, put this in your calculator. And what are you going to get? You're going to get root 3 with a phasor of -5. So it should always be VAB divided by square root 3 with a phasor of 30 or -30, depending on ABC or ACB. Yes. That you could just remember it like that. So that's a shortcut if you want to remember it like that. But then it just feels like you're just pulling the number out of thin air. Then again, you always feel like you're pulling numbers out of thin air. So if you want to memorize it, you can just skip straight to this part. I don't believe they will deduct points. So for negative, square root 3 with a phasor of -30 degrees. What's the value of VAB? Here. This is VAB. 3 with a phasor of 25. Let me just make that a bit clear. It says VAB. It says BC. And this is CA. So if you put that in your calculator, you're going to get square root with a phase of -5. And now, you can now find, using this graph again, VBN and VCN. VBN is going to be VAN, where the phase is the phase of VAN minus 120. Right? So VBN is just going to be root 3 with a phase of -125 degrees. VCA is going to be CN is going to be much the same. VAN with a phase of delta VAN plus 120 degrees. That's going to be root 3 with a phase of 115. Everyone know how we got that? You can also just calculate it again. You can just do the same thing for all of these around and around, but you'll just get this over and over again. So just subtract and add 120. They don't care. You can do that. So now we can now draw the Y configuration, right? So draw your Y. This is C. This is B. This is A. And this is N. Positive, minus, positive, minus, positive, minus. This here is going to be root 3 with a phase of 115. This is root 3 with a phase of -125 degrees. And this is root 3 with a phase of -5 degrees. There's your Y. All right. So, next part of the question. What's this? Oh. Next part of the question, compute the line currents I1, I2, and I3. So it doesn't say here. Yeah, it already says here. So I1 is going to be the current traveling out of A. I2 is going to be the current traveling out of B. And I3 is going to be the current traveling out of C. Pretty straightforward. I love water. So what is the line current? Well, what we can do... All right, let's look here for a second. So we're going to have some value, and actually, you know, let's just redraw the entire circuit. Fuck it. So we have A, B, and C, right? quick question. All right, what's your question? No bold plot on the final. No bold plot on the final. So if I redraw this entire circuit for you, this is ZT and ZL. ZL, ZL. And this is also N. It is ground. Right? So if you look at these, all of these three phase lines look identical. That's because they are. So what we could do is we can just take one of these. Let's take A. This is I1. This is I2, I3. This is B, C, and A. Let's take A, right? So we're going to have root 3 with a phase of -5 degrees, right? It's going to come out into a Z line, I don't know why it's a ZT load, into the Z load, and then they're both going to connect to ground. So it's effectively a connection to each other. What is this? This is just a circuit. This is the easiest circuit on planet Earth. V is equal to IZ. These Z's are in series. You just add them up. So therefore, Z combined, let's do, just combined, is going to be ZT plus ZL, which is right here. So that's 2 plus 5I plus 8 plus 3I. 10 plus 8I. Or J. There you go. Now you just plug in your numbers. Nothing special here. -5 over, what's that? 10 plus 8I is going to be, oops. Now put these in polar form and you'll see why in a second. It's a 0.135 with a phasor of -44 degrees. Now you won't believe this. You could do all of the line currents for all of the other ones, or I2, which is B, is just going to be offset by 120, and so is I3. By how much? You won't believe it, but it's the exact same chart as before. So this is going to be 0.135. 0.135. The only thing that changes in the phasor. In this case, it's going to be 120 off, so -164 degrees. And it's going to be 120 addition, so it's going to be 76 degrees. There are the line currents. Does anyone have any questions? Anything confusing? Did I go too fast? I'll take that as a no. All right, now let's compute the current through each voltage source in the delta configuration. So let me pull up the question here. So what it is asking through is in the delta configuration, right? So you have like so. Whoops. This is A, B, C. What is the current IA? What is the current IB? And what is the current IC? Right? And so this is just going to be KVL. So let's look at A here. We have the current out. This is going to be I1. This is going to be I2, and this is going to be I3. Let's look at KVL. Kirchhoff's voltage law. Yeah. Right here at A. And what we have is, yeah, I'm deleting that just because of how cringe statement that is. All right. So what's coming in? IA is coming in. What's coming out? I1 and IC. Now let's isolate for I1. So you're going to have negative I1 is equal to IC minus IA. Let's flip those around. Yeah, there you go. Just rearranging it. And now you won't believe this, but you guess what we're going to use? The exact same damn chart. Let's bring that down here, except this time we're just going to be using IA. We're going to be using currents instead. So for this one, we're going to have IA is equal to the magnitude of IA, phase of 0. IB is equal magnitude of IA, and IC is equal magnitude of IA offset by those amounts. Let's move that a little bit down so I can fit that in here. E. There you go. So once again, you do the exact same formula. So that's going to be the IA, the magnitude of IA, times that's going to be 1 with a phasor of 0 minus 1 with a phasor of 120 degrees. And you just do the exact same thing. So now IA, or I1, divided by square root 3 with a phasor of negative 30 degrees is equal to IA. Does everyone follow that? It's the exact same step that we did in the first time. It's just with currents now. And you know, I'm going to move all of this to a new page. There you go. IA, in this case, it's going to be 0.078 with a phasor of negative 14. And you will not believe this. This is going to be crazy. But IB is offset by 120 degrees. And so is IC. That's going to be negative 120, so it's going to be 134. And this will be 106. Any questions? All right, perfect. That's it. Now, next question. Find the complex power consumed by each ZT impedance in the transmission line. So you might be aware the complex power, let's say the complex power going through A is going to be VRMS IRMS conjugate. I believe it's conjugate. That's what it's called. Now, apparently people got confused about what this RMS stuff is. V peak, that's what we always use, is equal to 1 over square root of 3 VRMS. Sorry, not square root of 3, square root of 2 VRMS. That's it. I of peak is 1 over square root 2 of IRMS. That's it. There's nothing more to it. If you get a question in RMS, change it to peak. Just using this formula. That's it. There's nothing more to it. There's no like hidden stuff to it. Now, if you have IRMS star, what that means is, say if you have 5 with a phasor of -10, when you have a star, that makes it to 5 with a phasor of 10. That's it. It just turns a negative into a positive. Is that clear? Any confusion? I thought not. So let's move all of these formulas to the side here. Let's do stuff on the right. Now, here it's asking the power consumed by each ZT. So if you check that here, that's going to be this load here in the middle. So for that, we need to know the voltage drop across ZT, and we need to know the current passing through ZT. We know the current passing through ZT. That's just current passing through line 1. We just need to find the voltage. Let's draw a circuit out. This is going to be ZT. This is ZL. Now, believe it or not, this is a voltage divider. You can just voltage divide. So the voltage over ZL is going to be VAN. It's going to be VAN minus V1 here. Let's call this V1. You know the voltage for divider, so that's going to be VAN ZL over ZT plus ZL. What's that? Anyone know how to do that? Yeah. What's AN again? Oh, it's been a while. VAN is square root 3 with a phasor of -5. You can also do it the long way. Yeah. If it's about magnetic circuits, then probably ask me tomorrow, because after this I'm busy. So, but tomorrow just DM me and I'll help you out. Okay, awesome. So VAN is square root 3 with a phasor of -5. So VAN is equal to root 3, phasor of -5. Oops. So now VAN times VZL, which is too much copying. All the data is at top. So ZL here is 8 plus 3J. ZT here is 2 plus 5J. So ZL is 8 plus 3J. And underneath, it's going to be 10 plus 8J. It's just sum of them. So this is going to be 1.06 minus 0.453J, right? And once again, IRMS is just a line current? No, the line current is I peak. You have to convert it into IRMS. Remember this, right? Okay, so now that we have V1, all we have to do is V answer minus V1, or sorry, VAN minus V1. So that's going to be square root 3 with a phasor of -5 minus that. That's the voltage drop. complex, sorry, phasor form, and we're going to get that the voltage drop over ZT is 0.728 with a phasor of 24 degrees. Let me just double check my work here. Yes. Whoa, complex is here. Oh. Yeah, once we'll get through ELE, we'll focus on calc. I'm no mood. Anyway, so our current through line 1 is going to... What's our current through line 1? Is going to be 0. This dude. So I1's going to be 0.135 with a phase of negative 44. We already know this. And now we just implement this. So this requires VRMS and IRMS, but we have V peak and I peak. Thankfully, we can use these formulas. If you just use these formulas, you just substitute, you get 1 over 2 V I star. See? RMS is not that difficult. So 0.5 times, how do you get VZT? Is VAN minus V1. Sorry, let me write this here. VZT is equal VAN minus V1. Because we know the voltage. Yes, I'm using a drawing tablet for this. Oh, yeah. Unfortunately, this drawing tablet is the easiest one. I just got used to it over a long time. All right, have a good one. Okay, so the complex power is going to be half of VI star. So the voltage here is going to be 0.728 with a phasor of 24. And then times 0.135 with a phasor of 44. Remember that conjugate. You have to convert it into conjugate form. So let me just write that down so that people don't get confused. I1 star is equal 0.135 with a phase of 44 degrees, not negative 44. And so our complex power is going to be 0.04914 with a phase of 68. Now, you won't believe this, but this is the exact same complex power for all of the lines. They do not change in phase. This is the one thing that doesn't change in phase. So don't change the phase by 120. They're all 0.04914 with a phase of 68 degrees. And the unit is VA. Any confusion? Any questions? This might be a stupid question. Okay. What's your question? How did I get I1? That's from the previous question here. B. You just take one of the lines, you know the impedance through it, you know the voltage through it, you find I. Okay. Last question. So, wait, is there any other questions about this before I move on? I'm going to save this. ELE302 tutorial for final. The last part I did? Yeah, sure. This here? Okay. So if there are no other questions, I will move on to the last question. Or the last question on the final. Oh, one question? Sure, what's up? Why is the angle for SA, SB, and SC the same? If you calculate it, if you just change this with VBN and line and currents 2 and 3, you'll get the same answer. You could probably figure out the reason why, but I haven't. I just know that if you plug in the different, they're not constant, but they're the same. SA is equal SB is equal SC. If you start with different, yeah, they have the same angle and they have the same magnitude for every of them. Yes. If you try doing this question with I2 and VBN, you'll get the same answer. Okay, last question. We're almost there. This one is probably the easiest because you should know how to do this. Fourier. Sorry, 1 second.